Welcome to part one of one-dimensional kinematics. So I guess what we should probably start with is just basically defining what kinematics is. So anytime you see that prefix K-I-N-E, kina, right, you want to think about motion, right? So, you know, from middle school science, you guys have learned about kinetic energy, right? What's kinetic energy? Well, it's the energy of motion. So anytime you see that K-I-N-E prefix, it's indicating that motion is involved, right? If you look at kinesiology, well, it's kinesiology, right? It's the study of how the human body moves, right? Trying to maximize that. So kinematics is your basic, most simplified description of motion in physics. So it gives us how fast is it going? How far did it go? How much time did it take? So it gives you very basic information as far as what is that object doing, right? So it's your most bare bones explanation of the movement of an object. So whenever we're talking about motion, right, we're talking about the change in an object's orientation or position. So we'll cover all different types of motion in this class, whether it's translational motion, an object moving from point A to point B, or rotational motion, an object rotating in a circle. And the path that it follows is what we call a trajectory. So just get used to that term. We're going to throw that out there a lot. Now, we model the motion of an object in several different ways. In the next video, we'll cover modeling motion graphically. That's going to be one of the huge ways. But one of the most basic ways is through the use of a motion diagram. Now, motion diagrams are very simple to understand. They're made simply so that anyone can look at a picture and go, okay, I understand what's happening. Is this thing speeding up? Is it slowing down? Is it moving at a constant speed? So basically, if you were to look at this image here of the kid on a skateboard, every time that you see the image of the kid, an equal amount of time has elapsed. So notice, so let's call this time equals 0 seconds, time equals 1 second, time equals 2 seconds, time equals 3 seconds. So between 0 and 1 seconds, he travels a certain distance. Between 1 and 2 seconds, he travels that same distance. Between 2 and 3 seconds, he travels that same distance again. So that tells us that in equal time intervals, he travels an equal distance, therefore he's got to be moving with a constant speed. If, for instance, we look at this jogger here, notice what happens. Again, this would be time 0, time 1, time 2, time 3. Between 0 and 1, she covers a very small distance. Between 1 and 2, she covers a larger distance. Between 2 and 3, she covers an even larger distance. So that tells us that as time is going on, she's covering more and more distance per second elapsed, which means that she has to be speeding up. Lastly, if we look at this car here, and again, time 0, 1, 2, 3, between 0 and 1 seconds, the car travels some distance. Between 1 and 2 seconds, the car travels a lesser distance. And between time 2 and 3 seconds, the car travels an even lesser distance, right? Which tells us that as time goes on, it covers less and less distance per 1 second interval, right? So that tells us that this car is coming to a stop, right? The car is slowing down, right? And so the nice thing about these motion diagrams is just by looking at them, you can tell what's happening, whether the object's speeding up, slowing down, or moving at a constant speed. We'll skip this one until we get to two-dimensional. So let's say we've got these scenarios. We've got two cars, cars A and B. And we're to assume that there are equal intervals of time between the frames of both videos. Right, so this would be time equals 0, time equals 1, time equals 2, time equals 3. This would be time equals 0, time equals 1, time equals 2. Well, just by looking at them, which car travels the furthest in each second interval? Well, it would be car B, right? So car B is going faster. Now, what can we say about the overall speed of both cars, though? Well, we could say that both cars are traveling with constant speed, right? Both cars cover identical distances per time interval. Just car B covers greater distances per time interval, right? So both are traveling with constant speed, but car B is traveling with a greater constant speed. Now, we can boil down our motion diagram even further. right? If you're drawing out these motion diagrams, you don't necessarily want to draw, 5 instances of a car. So what do? We do what we call a particle diagram. So basically what we do is we imagine that all of the mass of that car can be condensed into a single point, right? So now, if we were to draw a motion diagram of a car stopping, like we saw earlier, instead of drawing the car 4 different times, right, we can just represent the car as a single particle, right? So it makes your life easier, right? So these two diagrams, both the motion diagram of the car stopping and the particle model, both show the exact same thing, right? They show a car that is slowing down. All right, so in example 1.2, we have 3 motion diagrams that are shown, which is a dust particle settling to the floor at a constant speed, which is a ball dropped from the roof of a building, and which is a descending rocket slowing to make a soft landing on Mars. So go ahead, pause the video, see if you can figure these out before continuing. All right, so let's go through these one at a time. If we look at diagram A, what do we notice about the distances between, or the distances traveled in each time interval? Right, we notice that the distances are increasing as time goes on, right? Between 0 and 1 seconds, it travels a little bit. Between 1 and 2, it travels a little further. Between 2 and 3, further, and so on, so on, so on. So what does that tell us about the object? Well, it's speeding up. So if we're looking at which one of these scenarios is an object speeding up, well, it would be a ball dropped from the roof of a building, right? Because it's being accelerated by the force of gravity. Now in B, notice that it covers an equal distance per time interval, right? So every second it travels an equal distance, right? That tells us that it's falling at a constant velocity, a constant speed. So we would have to assign that particle model to the dust particle settling to the floor at a constant speed. And lastly, part C, notice that the amount of distance traveled decreases as time goes on, right? So between 0 and 1, it travels a great distance. Between 1 and 2, a lesser distance. Between 2 and 3, a lesser distance, and so on and so on. So that tells us that this object is slowing down. So that would best match a descending rocket slowing to make a soft landing on Mars. Now, we talk about position a lot. Keep in mind, though, that when you're talking about position, there has to be some reference point, right? You can't give your position without referencing where you're measuring that position from. So, for instance, I don't know, let's say, your friend calls you and asks you where you are, and you say, I'm 4 miles. Well, does that tell your friend anything about your position? 4 miles from where? 4 miles from the school, 4 miles from their house, 4 miles from Wendy's, right? There needs to be some origin that you are using as your 0 point, your reference point, right? And so if you look at figure 1.7 there, notice that anything to the left of your reference point is a negative position, anything to the right of your reference point is a positive position, right? So you want to throw out kind of what math has taught you about negatives. A negative in physics simply implies direction. So if you have a negative position, it's simply saying that you are to the left of your reference point. If you have a positive position, it simply says that you're to the right of your reference point. So it just indicates direction. Now, in physics, we're going to deal with 2 different types of quantities. Things can be vector or they can be scalar. Now, scalar quantities only have magnitude. And you're going to hear that term a lot. Magnitude simply means a numerical size. So if, let's say, we're talking about your most common your most common scalar quantity that we use, which is speed, right? It would be 60 miles per hour, right? So it just gives you the magnitude, the numerical value, the size of your speed. Whereas your vector quantities, they give you more information than your scalars do. they don't just tell you the magnitude, the numerical value, but they also tell you the direction in which the object is traveling, right? So your scalar quantities give limited information, whereas your vector quantities give you much more. So the vector quantity version of speed is velocity, right? And so speed simply says the object is going 60 miles per hour. So it tells you how fast it's going, but it doesn't give you a full picture of what's happening. Now, when you're talking about the object's velocity, well, it would be 60 miles per hour east, or to the right, or left, or whatever direction it's moving, right? So you get a better idea of what that object is doing. You don't just know how fast it's going, but you also know which direction it's going. So your vector quantities include both magnitude and direction, whereas your scalar quantities are simply a magnitude. So your common scalar quantities are distance and speed, and your vector quantities are displacement, velocity, and acceleration. So all of those include direction. Now, we do want to differentiate between displacement and distance. Now, a lot of times we're going to use those terms interchangeably just because often they are the same thing, but in the back of your mind, you want to keep in mind that there is a distinction, right? Your displacement is your change in position. So how far from where did you start did you end up? And it's a straight line between those 2 points. Whereas your distance is the actual path that you took. So, for instance, take a look at the image right there. So that the blue arrow represents the path taken by, let's say this is a person on a hike. So he starts off and he takes that curvy path, right, and ends up all the way down at the bottom, right, at the head of the arrow. So the distance he traveled might have been, let's say that represents 16 miles. It was a 16-mile hike. But that's not his displacement. His displacement is represented by that green arrow. How far away did he end up from where he started? And that may only be 4 miles, right? So displacement and distance are not necessarily the same thing, right? If you're on a hike and let's say you go 4 miles this way, 4 miles this way, 4 miles this way, and 4 miles this way, well, the distance you traveled is 16 miles, right? But what's your displacement? Well, if you ended up back where you started, your displacement is 0. And sorry, I'm trying to get a better camera so I can actually use the board a little better. Just bear with me for now. All right, so let's say we got Sarah. She starts at a positive position along the x-axis. She then undergoes a negative displacement. What can we say about her final position? All right, so let's say this is our 0 point. We don't know where, and this is your positive, right, and this is your negative. Well, if this is your 0 point, we just know that she starts somewhere along this positive axis. Now, do they give us enough information to even determine what her final position is? We don't know where along the positive x-axis she started, and we don't know the size of that negative displacement, right? So her position could be positive or it could be negative. So again, if this is a 0 point, let's say Sarah starts here at this positive position, and she undergoes just a small negative displacement. Well, she's still on the positive position side of your 0 point. Right, so she could be positive position. Or she could start here and undergo a great negative displacement and end up on the left side of your 0 point, right? In which case her position would be negative. Right, so we don't know enough information to determine what her final position is without knowing where along the positive axis she started and how great that negative displacement was. All right, so the last thing we want to talk about real quick is speed and velocity. So again, we talked about it earlier. Speed is a scalar quantity. It simply tells you how fast something is going, whereas velocity is your vector quantity, which tells you not just the speed, but also the direction. Now, if we have an object that is moving in uniform motion, it means that it's moving at a constant speed, right? Uniform means consistent. So the formula for constant or average velocity is simply how far did it travel divided by the amount of time it took. So v is velocity, delta x is your change in position, and delta t is the time interval. So how far did it go, and how long did it take? Right, so that's your constant velocity equation, or also used for average velocity. Now keep in mind, if there's acceleration, you cannot use this equation. Right, so avoid wanting to use this equation when you don't see the term constant in there. Alright, so we've got this example where albatrosses are seabirds that spend most of their lives flying over the ocean looking for food. With a stiff tailwind, an albatross can fly at high speeds. Satellite data on one particularly speedy albatross showed it 60 miles east of its roost at 3 p.m., and then at 3:15 p.m. it was 80 miles east. What was its velocity? Alright, well, it traveled 60 miles in 15 minutes. So you could find its velocity in miles per minute by taking, it traveled 20 miles in 15 minutes, right? Because it went from 60 miles east to 80 miles east. So you take your 20 miles divided by the 15 minutes, that gives you your speed, your average velocity in miles per minute. And if you want me to work that one out during the live session, I will. But keep in mind, right, there's a difference between something moving at constant velocity and an object's instantaneous velocity. An instantaneous velocity is how fast was the object moving at any given moment in time. So for instance, if, let's say you traveled from here to Austin, and it took you 2 hours, right? Well, you could use the distance from here to Austin and the 2 hours that it took you, and you could find the average speed at which you traveled. Now, were you traveling that speed the entire 2 hours? No, sometimes you were blasting at 90 down the highway, which don't go 90 down the highway. Sometimes, you were sitting at light, sometimes you were sitting at traffic, so your instantaneous speed, your instantaneous velocity changes, right, throughout that trip. So keep in mind there's a difference there between your average velocity and your instantaneous velocity. And then acceleration. Your acceleration is, well, a change in velocity, right? So if your velocity changes, you are accelerating, right? And acceleration can be positive, acceleration can be negative, right? So keep in mind, when we're talking about velocity, we're talking about speed and direction. So when we're talking about acceleration, acceleration is any change in velocity, meaning any change in speed or any change in direction. Right, so an acceleration can be an object speeding up, it can be an object slowing down, or the one that people always forget, it could be an object changing directions. So by definition, anything going in a circle has acceleration. Take a look at the units. We're going to be using meters per second squared, seconds and kilograms. These are going to be your SI units, so make sure you're comfortable with those. Now, the last thing we want to look at is this idea of relative motion. Motion is all relative based off of the observer. So, classic example here is, take for instance, let's say you're sitting on a train, and right in front of you, you've got yourself a bottle of water on the table, and the train is moving down the tracks. Well, you're sitting there, you got your bottle of water on the table in front of you. Relative to you, is that bottle of water moving? No, right? Relative to you, that bottle of water is stationary in front of you on a table. But let's say that you've got some dude who's standing on the tracks watching the train go by. And he manages to see that bottle of water in your window pass by. Well, relative to him, that bottle of water is traveling at whatever speed the train is. Right? So the frame of reference matters when you're talking about motion. Right? Relative to me, if you were in class right now, you would be sitting stationary at a table. Right? But then if we go up to the International Space Station, well, they're orbiting the Earth at high speeds. They're going to see you moving at high speeds. Right? So it's all relative to the observer. And keep that in mind next time you're driving down 377. Right? If you're driving down 377, there's a train going the same way. The train looks like it's moving very slowly, or it could look like it's moving backwards depending on your speed, right? But is it? Well, it depends on your frame of reference. And that's something we can talk about in our live section. I encourage you to think about that, ask questions. Now, in the next recorded video, I'm going to try to get up by, hopefully by Wednesday or Tuesday night, we will cover graphing. So I just wanted to basically hit, some of the major terms for you guys, some of the major ideas. And again, let me know if you have any questions. See y'all soon.